Okay, so the next thing we're going to take a look at is how we can relate gases and the behavior of gases to some other principles that we've seen previously. And what we're going to take a look at now is something known as buoyancy. And we'll try to relate that to gases and how all of that is kind of tied into fire and fire behavior as well. So as you know from experience, if we have, for instance, this container here, let's say that it's filled with water, and we place an object in or onto this container full of water, well, a couple things can happen. This object that we place can either sink or it can float. And depending on what it does, allows us to draw some conclusions about both the object and the water. So for example, if this object floats on the surface of water, then what we can conclude then is there's a difference in density, and specifically what we can say then is that the object is less dense than the water. Okay, and we've seen this previously. We did a couple experiments with density, etc. So whatever is less dense will float on something that is more dense. All right, we know that from experience. So what we also know then is that when this object floats on here, this is exerting some sort of a force on the surface of the water. But what also happens is, according to what we discussed previously, is that the water is also exerting a force in the other direction on that object itself. And that is what causes, in this case, this object to float, right? So we have opposing forces um, from the object onto the surface of the water, and then the water going in the opposite direction. So what we've just illustrated here is this idea of buoyancy. And what we can describe buoyancy as being is the upward force of exerted by some fluid. In this example, the fluid is just liquid water that opposes the weight which is the force due to gravity of that object, of an object. A most object is this in this case. All right, so when we talk about the buoyant force, this is what we are referring to. And again, this is something that we've seen previously. It also can be applied to gases as well. Okay, so we talked a lot in this section about gases, kinetic molecular theory, the gas laws, how the gases behave, etc. Now we're going to tie this into the behavior of gases. And if you think about, an instance where you have a room, for example, and you have fire that's burning in this room like this, obviously when this fire heats up and it produces these hot gases. Okay, the hot gases that are produced, whether it's carbon dioxide, water vapor, etc., these are less dense than the other gases that are present in the room. And as a result, those, according to this principle of buoyancy, those hot gases will rise due to that buoyant force. U-O can spell correctly. Okay, so the upward force exerted by those other gases, those cooler gases, is stronger than the downward forces of those hot gases. In other words, the hot gases are less dense, and as we know from above as well, the less dense substance will float on substances that are more dense. And these are the reasons why the hot gases will rise to the top of this room, for example. Now, what this results in then, because now we have gases rising to the top, other gas molecules, cooler gas molecules, will fill in that void in all directions. Okay, and that could be, gases that fuel the flame, like oxygen, for example. All right, so in other words, what's happening here, right, is you have gases being pulled in due to the movement of those hot gases rising as a result of that buoyant force. So what we are explaining, what we're seeing here then is a phenomenon known as air entrainment. And this is the drawing of air into the fire. Or a fire plume, for example. And this is due to what we just described, which is the buoyant flow of plume. So this process entraining the air as hot gases rise due to the buoyant flow, the buoyant force, causes other gases to move in, leading to what's known as air entrainment. That other gases moving in can sustain the fire and cause all sorts of downstream things to happen. So again, here we're sort of relating a couple of the other concepts we've seen before. So density, for instance, now we're introducing the term buoyancy to that to help explain that process. And we're now relating it to gases, which is what all this section is about. So if we have just to kind of to tie in some other concepts and just to introduce some things that you might see further down the road in your fire investigations, fire dynamics courses. So if you have here a very simple situation, you have a room, so you have the ceiling, got the walls and the floor as a chair. In the middle of the room, there's a fire, let's say burning in it. So what we just discussed was the fact that the hot gases here will lead to those hot gases rising. So let's label that B, and then B would be the buoyant fire plume. And as we've just discussed, also the movement of that air upwards as it rises due to the lower density of the hot gases would cause other gases to move in by entrainment. So we'll refer to that as A, and A here will be our entrained air. Again, due to that buoyant fire plume rising. And as that plume rises, the hot gases rise. They're going to hit that ceiling. And what's going to happen is they're going to flow along the ceiling. They can't go any further than that. We'll label that C. And that is referred to as the ceiling jet. So that's the movement of air now, hot air particles, hot air gases, as they hit that ceiling, they start spreading out in all directions. And eventually, as they hit the walls, they're going to start moving down the walls. label this as D on either side or on all walls of the room. Imagine that this is the fire is happening at the very center of the room. So D there would be the flow along the walls. So this is what's known as a convective flow pattern that results from a fire that's occurring, in this case, in a closed room, and that happens, the movement, the flow pattern here results ultimately from those hot gases that are rising due to the buoyant flow as they're less dense than the cooler particles, the cooler gases that are being entrained at the base of the fire.